Alright, let's make this a little more complicated. Instead of a unit circle, let's make a circle with a different radius other than 1. Let's make the radius 4 instead of 1. So here, the value of cosine theta and sine theta are going to be the same. But if we pick one point on the circle, figure out what angle is made, and we want to figure out what distance this corresponds to on the x-axis and what distance this corresponds to on the y-axis, we can still use sine theta for the y-axis and cosine theta for the x-axis, but we have to multiply those values by the radius of the circle, which is also the hypotenuse of a triangle. So here's our radius of the circle, also the hypotenuse of this right triangle, and we can say that the bottom side that corresponds to the x-axis is the hypotenuse times cosine theta. We can say that this side going up, which corresponds to the y-axis, is 4 sine theta. Because look, check it out. This side length here is exactly this length here. So we're just taking this line and moving it over there to make a triangle. This chapter is all about triangles. Here's another example. Say we have a circle with a radius of 8, and we want to figure out the x and y coordinates at this point on the circle where there's an angle of 80 degrees. So theta is 80 here. And we want to know what are the x and y values of this point. And I want to show you that we can think about it as a triangle where this side is the y value and this, that side's the y value and this side is the x value. And that length up there is the same as this length down here. So I'm just taking this length, putting it down here to make this beautiful right triangle. We know that the hypotenuse is 8 because it's the same as the radius of a circle. And since we know the hypotenuse, we can say that this side is 8, the hypotenuse, times sine of 80. And notice that we multiplied by sine the hypotenuse by sine of the angle that we know to find the side length opposite the angle that we know. This side here would be the adjacent side to the angle we know of 80 degrees. And this pattern is the same for any triangle you look at. To find the opposite side length, you multiply the hypotenuse by sine theta, and to find the adjacent side, the side that's involved in the angle you know, you multiply the hypotenuse by cosine of theta. So alright, let's do this adjacent side here. This side would be the hypotenuse 8 times cosine of the angle that is made by that side, which is 80. And we get reasonable answers. Okay, so now let's look at some triangles that have been ripped out of the unit circle, or a bigger circle. In any case, no matter what orientation the triangle is at, we can find the opposite side to the angle we know by multiplying the hypotenuse by sine of the opposite angle. So let's identify the hypotenuse. This is the longest side of the triangle. We know that the longest side is opposite to the right angle here. So here's our hypotenuse. So let's find A, the side opposite to theta. A is the hypotenuse times sine, because it's the opposite side, of 35 degrees. If we want to find side B, we take the hypotenuse times cosine of theta. And here we use cosine because B is the adjacent side to this angle that we know. This side is included in the angle. Here's another example. Here we have a slightly smaller angle that we know, and the hypotenuse is pretty short, 0.31. So let's say we want to find angle A first, or side length A. To do that, we know we have to take the hypotenuse and multiply it by either sine or cosine of 22 degrees. Here's how we figure out which one to pick. We have to figure out if this side A is opposite or adjacent to the 22 degrees. And because it is included in the angle of that 22 degrees, we know it's adjacent. Because it's adjacent, we pick cosine. And B is the opposite side. So B is the hypotenuse times sine 22. So now let's use these skills in some physics type problems. What I've drawn here is a displacement vector. And here's the story behind this. There's a guy, this is a river by the way. So there's like water flowing this way. Here's a guy, he's been swimming. He started off here, and his displacement is represented by this vector. And he's trying to reach the other side, but the current's kind of pushing him a little bit. So his total displacement is, say, 73 meters. And we want to figure out how far actually toward the other side has he gone. So that's basically saying what is the y component of his displacement. And we can identify that as this distance here. And if we know that, say, the value of theta here is 40 degrees, we can use the same kind of approach to find just how far this guy's come toward the other side. We'll call that distance y. So here we have to realize that we have a triangle. One side is the side length we're trying to find. Here's another side, and then here is the hypotenuse. Because here's our right angle, the hypotenuse is on the opposite side. So we can do the same thing we were just doing. To find one side of a triangle, we take the hypotenuse times either sine or cosine of theta. And here, y is the opposite side. So to figure out whether we're doing sine or cosine, we figure out whether we're finding the opposite or adjacent side. Here it's the opposite side, so we pick sine of theta. And here we know the hypotenuse happens to be 73, and theta happens to be 40. So the y value of his displacement is 46.9. And we could also write that vector over here and if we wanted to find how far down the river he's gone, we would be finding this side length of the triangle. So I'm writing these as vectors because what we just found is the vertical component of his displacement vector, and what we're about to find is the horizontal component of his displacement vector. We can take any vector and decompose it into its y and x components. And the x component here is the hypotenuse times cosine of theta. We use cosine because this is the side that's adjacent to the 40-degree angle. Hypotenuse times cosine of 40. And we find that's 55.9. And here's something important to realize. We could either say that he's displaced himself 73 meters in this direction, or we could say that he's displaced himself 46 meters in the y direction and 55 in the x direction. Both of those are saying the exact same thing. Both of those are entirely valid. But in the second description, it's basically after we've decomposed this vector to look at just its x component and just its y component. And here's an amazing thing. This works with velocities as well as displacements. It's the exact same approach. Just take a vector, make it into a triangle, and do the hypotenuse sine times cosine or sine of theta. An example here, using velocities. Alright, we got a taxi. It's trying to take you to work, but he's doing like a shortcut, quotation marks around shortcut. And at some instant, you're not heading exactly toward work, but at some angle relative to work. And this taxi driver might be going 50 miles an hour, but you're curious, what is the actual velocity toward your place of work? So I guess here would be the x component of the velocity. So this Vx is what we're really interested in. And the 50 miles an hour that the taxi is actually going is our overall velocity. And note how I made the Vx exactly on the same vertical line as the 50 vector. I would do the same thing with the y component of the velocity vector. I would bring this vector, this Vy vector down so it's exactly even with that overall velocity vector of 50 miles an hour. And I do that so we can make beautiful right triangles. And let's make this a little bit complicated. Let's say that we know this angle is like 71 degrees. And if we want to make a triangle with that angle in it, this becomes our triangle. Doink, doink, doink. And we just have to realize now that this side on the bottom is Vx. So we've basically just taken Vx up here and we've moved it downward without changing the length of this vector, so the magnitude is the same. We've just kind of placed it here instead of up there. And that doesn't change anything about it. It doesn't change the size of that vector and it doesn't change the direction. But it does make it part of a beautiful little triangle. So just, let's look at this triangle. We know this hypotenuse here, this side length, is the overall velocity, which is 50. This side on the bottom is our Vx, and this side is our Vy. And we want to find Vx. Take just a minute to think about how you would do this, knowing this, that we've got this triangle here and using trigonometry. Hopefully you've decided to find it by multiplying the hypotenuse by sine of 71. And just here's an aside, FYI. Notice that we can never make any side length greater than the hypotenuse when we multiply by sine or cosine, because the value of sine or cosine always is between 0 and 1. So when we multiply sine or cosine by the hypotenuse, we always get a smaller value. So the rate of velocity in the x direction is 47.3 miles an hour. And just for completeness, let's find how fast he's going downward. What is the vertical component of this taxi's velocity? Here if we took hypotenuse times sine 71, now we're going to have to take hypotenuse times cosine 71, because this Vy is the adjacent side to the 71 degrees. So we could either say that the taxi is driving at 50 miles an hour in this exact direction, or we could say that the taxi is driving with a velocity of 47.3 miles per hour in the horizontal direction and a velocity of 16.28 miles an hour in the vertical direction.
Made with Doodlecast Pro.